Good morning, everyone. This is an audio recording for visually impaired student. Today, I am going to read a chapter from Organic Chemistry. Chapter is Organometallic Compound. Introduction: Organic compound in which a metal atom is linked directly to a carbon atom are called organometallic compounds. A large number of metal like lithium, sodium, magnesium, etc. form such compounds. The organic part is generally an alkyl or a aryl group. They are named simply by adding the name of the metal to the name of the organic group linked to the metal. For example, methyl lithium, ethyl magnesium, dimethylcadmium, diethyl zinc. The carbon metal bond in organometallic compound differ widely, varying from bonds which are essentially ionic to those which are largely covalent. Thus, the extent of the ionic or a polar character of the bond is largely determined by the electropositive nature of the metal. More electropositive the nature, more is the ionic character of the carbon metal bond. In general, the ionic character of the carbon metal bond follows the sequence C sodium potassium is more than C sodium, more than C lithium, more than C magnesium, more than C aluminium, more than C zinc, more than C cadmium, and more than C mercury. The reactivity of organometallic compound also depend upon the nature of carbon metal bond. Generally, larger the ionic character of carbon metal bond, more reactivity is the organometallic compound. However, compounds having intermediate ionic character are of greater importance because of their lower reactivity and selective nature of the reaction. Organometallic compounds are extremely useful for the synthesis of a vast variety of organic compounds. Apart from this, many of the organometallic compounds are commercially important as well as, for example, tetraethyl lead is extensively employed as an anti-knock compound. Organto compounds are used as an antioxidant in rubber product. Phenyl mercury acetate is used as a fungicide and disinfectant, and organoarsenic compound are used in medicines. Organomagnesium compound called a Grignard agent. Organomagnesium halide are extremely important reagent in synthetic organic chemistry. The reagents are commonly known as a Grignard reagent after the name of the discovery. Victor Grignard received the Nobel Prize in Chemistry in 1912 for his discovery. The general formula of Grignard reagent in RMGX or ARMGX, where R represent an alkyl group and AR represent an aryl group. Preparation: Grignard reagents are prepared in the laboratory by the action of an alkyl or a aryl halide on magnesium metal in dry ether. Alkyl halide plus magnesium in the presence of dry ether, it will give RMgX. Beside ether, THF, DME, or dimethyl ether of diethylene glycol, tertiary amine, etc., can be used as a solvent. In fact, THF considered as a best solvent since it increases the reactivity of an alkyl or a aryl halide toward magnesium. It is because of the reason that Grignard agent of less reactive aryl and vinyl halide are prepared in THF. Bromobenzene plus magnesium in the presence of dry ether, it will give phenyl magnesium bromide. Vinyl chloride plus magnesium in the presence of THF and heating, it will give vinyl magnesium chloride. Further, it has been found that for a given alkyl group, the easy of the formation of Grignard reagent is the order iodide is more than bromide is more than chloride. The alkyl or aryl magnesium fluoride are however unknown. For a given halogen atom, the order of reactivity is CH3x more than C2H5x more than C3H7x, etc. The formation of the Grignard reagent become increasingly difficult with increase in the number of carbon atom in the alkyl group. The use of tertiary alkyl iodide is avoided since they readily lose a molecule of hydrogen iodide to form an alkene. Tertiary alkyl chloride may then be used. Procedure for the preparation of Grignard reagent. Alkyl or a aryl halide is added slowly to a perfect clean and dry flask containing dry magnesium turning covered by a layer of absolute dry ether or THF. The reaction mixture is warmed a little when a exothermic reaction should soon start. If the reaction does not start within 5 minutes, a few crystals of iodine are added and the reaction mixture is warmed a little. A vigorous reactions soon set in and magnesium gradually dissolve, forming a cloudy solution of the Grignard agent. Precaution in the preparation of Grignard agent. During the preparation of Grignard agent, the following precautions must be observed. First, the apparatus should be perfectly dry and protected from moisture by using a CaCl2 guard tube. Second, all the reagent and solvent, for example, alkyl or aryl halide, magnesium metal, and ether must be absolute dry. Ether used as a solvent must be completely free from alcohol. This can be done by first washing ether several times with water, followed by dyeing over anhydrous CaCl2 for 1 to 2 days and subsequent distillation over sodium. Fourth, an atmosphere of dry nitrogen, free from oxygen and carbon dioxide, should be maintained throughout the course of the reaction. These precautions are necessary since Grignard agents are decomposed by moisture and react with oxygen and carbon dioxide to form alcohol and carboxylic acid respectively. The ethereal solution of Grignard agent thus obtained is generally used as such for various reactions by adding it the other reagent mechanism. The mechanism of the formation of Grignard reagent is still not certain. According to Kumbrook and Beckman, the reaction commences with the formation of small amount of magnesium halide and then proceed by a free radical mechanism. Rx plus Mg plus Rx, then it will give Rr plus Mgx2. Mgx2 plus magnesium, it will give 2 Mg radical X. Rx plus Mg electron X is equal to R radical plus Mgx2. R radical plus Mg radical X, it will give RMgx. This mechanism also elegantly explains the initiating effect of iodine, which may be ascribed to the formation of magnesium iodide from magnesium and iodine. Structure of Grignard agent. The structure of Grignard agent has not been finally settled so far. The recent research has shown that the actual structure vary with the particular Grignard agent and the solvent used for of its preparation. Grignard observed the evaporation of ethereal solution of Grignard reagent, resulting in the white solid having the composition RMGX.2 C2H5 twice O. They suggested that ether molecules were present as a ether of crystallization. X-ray analysis of these dietherates suggested that four groups are arranged tetrahedral as shown in formula first. Thus, formula first suggested that ether does not merely provide a medium for the reaction, but it also helps dissolve the Grignard reagent formed due to the solvation by ether molecule. This is spotted by observed that Grignard reagent can be prepared even in benzene solution in presence of the tertiary amine, which coordinate with magnesium like ether and thus dissolve it. Further, the formula first showed the Grignard reagent in the monomeric form, but physical study has revealed that Grignard reagent exists as a 1:1 complex of a dialkyl or diaryl magnesium and magnesium halide coordinate with molecule of ether. These two species are held together by a halogen bridge as shown in formula second. R2Mg Mgx2. It will give R2Mg plus Mgx2 and it will give 2 Grignard reagent. However, for the sake of convenience, the formula RMGX have been used to represent alkyl magnesium halide in the text. Reaction of Grignard reagent. The carbon magnesium bond in Grignard reagent is highly polar due to the large electronegativity difference between carbon and magnesium. 2.5 1.2 is equal to 1.3. Consequently, due to the greater electron density around carbon, the alkyl group in Grignard reagent act as a carbanion or a nucleophile. For example, it can attack any electron deficient center in other molecule. In other words, Grignard reagent chiefly undergo nucleophilic substitution or nucleophilic addition reaction. First, nucleophilic substitution reaction. Grignard reagent react with compound containing an hydrogen or a halogen atom. All such reactions involve the nucleophilic attack of the alkyl group of the Grignard reagent on the electron deficient center as shown below. RMgx plus AB, it will give Ra plus MgBx. Second, nucleophilic addition reaction. Grignard agent react with compound having a multiple bond to form addition product when when hydrolyzed yield as a variety of compound. In all such reaction, the addition of a nucleophilic group of RMgx R occur at the more electropositive end and the that of the MgX group at the more electronegative atom of the multiple bond. Synthetic use of Grignard reagent. Grignard reagents serve as extremely valuable starting material for the synthesis of the vast variety of organic compounds. They have attained a position in synthetic organic chemistry unrivaled by any other classes of compound. To illustrate this, some important synthetic applications of Grignard reagent are described below. First, alkenes. A. By action with active hydrogen containing compound. Active hydrogen compound such as water, alcohol, thialcohol, carboxylic acid, terminal alkynes, etc. react with Grignard reagent to form an corresponding to the alkyl or aryl group of the Grignard reagent. RMgx plus HB, it will give RH plus MgBx, where B is OH, OR, SR, OCOCR, NH2, NHR, NR2, etc. CH3 MgBr plus acetylene, it will give CH4 plus CH double bond CMgX. Since methane is evolved qualitatively when CH3MgI is treated with compound containing active hydrogens, therefore these reaction can be used for acetamation of OHNH2CH group in organocompound. This method employed is called the Zarivitin's method. Aryl magnesium halide also behave as a similar manner. Phenyl magnesium bromide plus water, it will give benzene plus MgOHBr. Second, by reaction with reactive alkyl halide. Grignard reagent react with reactive alkyl halide such as T-butyl chloride, benzoyl chloride to form alkanes. Methyl magnesium iodide plus tertiary butyl chloride, it will give neopentane plus Mg chlorine I. Second, alkenes. Grignard reagent being weak nucleophile do not react with simple alkyl halide. However, the compound containing more reactive halogens such as allyl iodide react with them giving alkene. Alkyl iodide plus CH3MgI, it will give T-butane plus MgI2. 1 butane plus MgI2. Third, alkyne. Grignard reagent react with terminal alkyne forming alkyne Grignard reagent. Treatment with alkyl halide give higher alkynes. Fourth, primary alcohol. By action with ethylene oxide followed by hydrolysis, Grignard reagent with ethylene oxide to form addition product which on hydrolysis with dilute hydrochloric acid form alcohol containing 2 carbon atom more than the alkyl halide. By action with formaldehyde followed by acid hydrolysis, when treated with formaldehyde, Grignard reagent form an adduct which on hydrolysis with dilute hydrochloric acid give a primary alcohol. Formaldehyde plus Grignard reagent, it will give addition product and then we will get the primary alcohol. By action with oxygen, primary alcohol are formed by passing dry oxygen through the solution of Grignard reagent followed by acid hydrolysis of the resulting addition product. N-propyl magnesium bromide plus half O2. It will give CH3, CH2, CH2, OMgx on hydrolysis. It will give and propyl alcohol. Fifth, secondary alcohol. A. By action with aldehyde other than formaldehyde followed by acid hydrolysis. Acetaldehyde CH3MgI, it will give CH3CH CH3OMgI. On hydrolysis it will give isopropyl alcohol. B. By treatment by treating an excess of the Grignard reagent with ethyl formate. The reaction takes place in two steps. Grignard reagent first react with ethyl formate to form an aldehyde, which is turn react with another molecule of Grignard reagent to yield an induct, which form a secondary alcohol on hydrolysis. 6. Tertiary alcohol. By action with ketone followed by hydrolysis. Ketone on hydrolysis it will give secondary alcohol, tertiary alcohol. Acetone on reacting with C2H5MgX and further followed by hydrolysis it will give 2-methyl 2-butanol. A tertiary alcohol having at least two similar alkyl groups may be represented by the interaction between an ester other than formic ester and an excess of the Grignard reagent. Proceed in two steps. Third, by reaction with acid chloride and anhydride, Grignard reagent react with acid chloride or anhydride to give addition product, which upon acid hydrolysis give tertiary alcohols. The reaction takes place in two stages. Ether. Grignard reagent react with lower halogenated ether to yield higher ethers. Monochloromethyl as ether plus CH3MgI, it will give ethyl methyl ether plus MgICl. 8. Aldehyde. When a Grignard reagent is treated with ethyl formate, an aldehyde is formed. However, with excess of Grignard reagent, the product obtained is a secondary alcohol. Ethyl formate plus RMGX, it will give on hydrolysis give the aldehyde. B. Aldehyde are obtained in a better yield if ethyl orthoformate is employed instead of ethyl formate. This is so since the formation of acetal in this case prevent the formation of secondary alcohol. Ethyl orthoformate in the on hydrolysis firstly it will give acetal and finally it will give aldehyde. C. Aldehyde may also be obtained by the interaction between a Grignard reagent and a hydrogen cyanide followed by hydrolysis of the adduct formed. Hydrogen cyanide plus Grignard reagent it will give addition product. On hydrolysis it will give aldehyde. 9. Ketones. A. By treatment with the alkyl cyanide followed by acid hydrolysis. For example, acetonitrile plus CH3CH2 MgBr, it will give CH3C CH2 CH3 double bond and MgBr. On hydrolysis, it will give ethyl methyl ketone or 2-butanone. B. By action with acid chloride. As discussed on page 83, equimolecular amount of Grignard reagent and a acid chloride give an addition product which form ketone on hydrolysis. If Grignard reagent is used in excess, tertiary alcohol are obtained as ultimate product of the reaction. 10th, monocarboxylic acid. Grignard reagent interact with dry ice to form addition product which on acid hydrolysis give monocarboxylic acid. 11. Ether. By action with ethyl chloroformate, equimolecular amount of Grignard reagent and ethyl chloroformate react together to form higher acid. Ethyl chlorate plus Grignard reagent, it will give addition product and finally it will give higher ester plus MgXCl. Thioalcohols. Grignard reagent react with sulfur to give an addition product which gives a thioalcohol on hydrolysis. RMGX plus X, it will give addition product on hydrolysis. It will give thioalcohol or ethane thiol. 13. Phenol. Aryl magnesium halide react with oxygen to form addition product which upon hydrolysis give phenol. Phenyl magnesium bromide plus half O2 in the presence of dry ether it will give phenoxy magnesium bromide. On further hydrolysis it will give phenol. 14. Alkyl cyanide. By interaction of Grignard reagent and cyanochloride or cyanogen. RMgX plus cyanogen chloride, it will give alkyl cyanide plus MgXCl. Excess of Grignard reagent is avoided since it will react further with alkyl cyanide to yield ketones. 15. Primary amines. Grignard reagent react with chloramine to form primary amine. RMgX plus NH2Cl chloroamine, it will give RNH2 plus MgXCl. Reasonable yield of primary amine is obtained only with the Grignard reagent containing tertiary alkyl group. Primary amine can also be prepared in satisfactory yield by the action of Grignard reagent on O-methyl hydroxylamine. 16. Sulfonic acid. On passing sulfur dioxide in a well-cooled solution of Grignard reagent, an addition product is obtained which on hydrolysis gives sulfonic acid. Sulfur dioxide plus Grignard reagent give addition product. After the on hydrolysis, it will give sulfonic acid. Dithioic acid. These are prepared by the action of Grignard reagent with carbon disulfide followed by acid hydrolysis. Carbon disulfide plus Grignard reagent, it will give addition product. On hydrolysis, it will give diothic acid. 16. Organometallic compound. Grignard reagent and inorganic halide interact with each other, resulting in the formation of other organometallic compound like C2H5MgBr plus HgCl2. It will give diethyl mercury plus 2MgBrCl. Again, for C2H5MgBr plus SnCl4, it will give C2H5 tetra SN plus 4 MgBrCl. Tert ethyl tin. Abnormal addition of Grignard reagent. First, addition to hindered ketone. If the Grignard reagent or a ketone contain branching at the alpha carbon, sometimes the useful addition product does not occur due to the steric hindrance. Instead, reduction occur in which a hydride ion is transferred from the Grignard reagent to the ketone via a six-membered cyclic transition state in a manner similar to Mirwin Pondorf-Verlet reduction. For example, when isopropyl magnesium bromide is added to diisopropyl ketone, the expected tertiary alcohol is not formed. Instead, the secondary alcohol, diisopropyl carbonyl, is obtained by reduction of the keto group. Reduction to alpha beta unsaturated compound. Alpha beta unsaturated carbonyl compound react with Grignard reagent to give 1,2 and 1,4 addition product. The orientation of addition is often controlled by steric factor. In general, substitution at the carbonyl factor favor 1,4 condition while substitution at the double bond favor 1,2 addition. For example, 1,2,3 triphenyl pro 2 in 1 on in the presence of pH MgBr and on hydrolysis it will give 1,2,3,3 tetraphenyl propane 1 on. In most cases, both products are formed, but alpha beta unsaturated aldehyde nearly always give exclusively 1,2 addition product when treated with Grignard reagent. However, the extent of 1,4 addition of Grignard reagent can be increased by carrying out the reaction in the presence of cuprous chloride or cupric acetate. This is called the conjugation addition and probably occur by free radical mechanism. Limitation of Grignard reagent. Grignard reagent suffer from the following limitations. Grignard reagent are sensitive to moisture, oxygen and carbon dioxide and anions must be protected from them. This makes the handling of Grignard reagent difficult. Second, Grignard reagent cannot be prepared from alkyl halide containing other reactive function group such as OH, CH, NH2COH, SO2, etc. Since they all react with them, only alkyl halide containing a few other groups such as R, OR, AR, X, etc. can be used to form Grignard reagent. Third, generally branching of the carbon chain near the functional group prevent the reaction probably due to the steric hindrance. For example, CH3MgBr or CH3MgI does not react with dibutyl ketone Similarly, if the Grignard reagent contains large alkyl group, the reaction is sometimes prevented again due to the steric hindrance. For example, isopropyl methyl ketone react with CH3MgI but not with tert butyl magnesium chloride. Fourth, compounds which are capable of enolizing liberate hydrogen with Grignard reagent. Keto group, it will give enol form in the presence of CH3MgI. It will give the final product. Nitro compound cannot be used in Grignard synthesis since they oxidize the Grignard reagent. Despite the above limitation, Grignard reagent are still the most important tool in organic synthesis. Organogen compound. Although organogen compound of the type R2-Zn are not commonly used in organic synthesis, they are particularly useful when milder reagents are required. Method of formation. Following method have been used for the preparation of organozone compound from alkyl halide. Alkyl iodide react with zinc copper couple in high boiling ether to form alkyl zinc iodide, which upon subsequent distillation in an atmosphere of CO2 undergo disproportion to give dialkyl zinc compound. Second, from a organoaluminum compound, treatment of trialkyl aluminum with zinc chloride give dialkyl zinc compound. This method forms the base of laboratory preparation of this compound. Physical properties. Dialkyl zinc compound have linearly geometry due to the sp hybridization of zinc atom. They are nonpolar, low boiling point or low melting point, soluble in organic solvent. The lower zinc compound are highly inflammable in air and hence are usually prepared and used undergo CO2 atmosphere. Chemical reaction. The chemical reaction of organogen compound are similar to those of the Grignard reagent, with the only difference that they are less reactive. For example, they do not react with CO2 and react only slowly with cyanide, keto, or ester. Some important chemical reactions of dialkyl zinc compound are discussed below. First, reaction with water. They readily react with water forming alkane. Second, reaction with alkyl halide. Dialkyl zinc compound do not react with primary and secondary alkyl halide. They react with only tertiary alkyl halide to form alkane containing a quaternary carbon atom. Third, reaction with acid chloride. They react readily with acid chloride to form ketones. Ketones are obtained in good yield because dialkyl compound react very slowly with them. Third, reformester reaction. When an aldehyde or a ketone is added to the solution of an alpha haloester in presence of zinc, an organogen compound is first formed, which then added to the carbonyl group is similar to the Grignard reagent to form a beta hydroxy ester. The reaction is called reformatory reaction and is a useful method for preparation of beta hydroxy ester or acid and their derivatives. Idomethylene zinc iodide. Idomethylene zinc iodide is an important organozone compound and is obtained by the action of zinc copper couple on methylene iodide. CH2 I2 plus zinc in the presence of diethyl ether, it will give idomethylene zinc iodide. It reacts with olefins to form cyclopropane derivatives. This reaction is called Sisman-Smith reaction and is used for the preparation of cyclopropane derivatives. The addition occur in a stereospecific sign manner according to following conserved mechanism. Organolithium compound. Compound in which lithium atom is directly bonded to the carbon atom are called organolithium compound. For example, methyl lithium, ethyl lithium, etc. Organolithium compounds are more reactive than Grignard reagent and also undergo a few additional useful reactions. Therefore, they are widely used in organosynthesis these days. Formation of alkyl lithium. First, by reaction of an alkyl halide with lithium. Alkyl lithium are generally prepared by treatment in alkyl halide with lithium in hexene, benzene, or many other hydrocarbon solvents at a low temperature in an inert atmosphere of nitrogen or argon. For the preparation of alkyl lithium, hydrocarbon solvent are preferred over other ether since the use of ether not only encourage Woods reaction but also react with it. Second, by metal-metal exchange, alkyl lithium can be readily prepared by the replacement of one metal by another. For example, diethyl mercury plus 2Li, it will give ethyl lithium plus Hg. Chemical reaction of alkyl lithium. The C-Li bond is more polar than CMG bond. Therefore, alkyl lithium are more reactive than the Grignard reagent. Except a few differences, their chemical behavior is similar to that of the Grignard reagent. Some of the important chemical reactions are discussed below. First, resemblance with Grignard reagent. They resemble Grignard reagent in most of their reactions. Some of the reactions are: first, formation of hydrocarbon like Grignard reagent. They react with compound containing active hydrogen to form the corresponding hydrocarbons. For example, methyl lithium plus H2O, it will give methane plus LiOH. Second, formation of primary Scandian tertiary alcohol, primary alcohol by action with formaldehyde. Formaldehyde react with alkyl lithium, it will give primary alcohol. Like Grignard and alkyl lithium compound are also react with ethylene oxide to form primary alcohol containing two carbon atom more than the starting alkyl or aryl halide. B. Secondary alcohol by action with aldehyde other than the formaldehyde. Third, tertiary alcohol by action with ketone. Formation of ether by action with an monochloroether. In the presence of hexane, it will give ethyl methyl ether. Fourth, formation of aldehyde by action with ethyl orthoformate or hydrogen cyanide. Hydrogen cyanide plus CH3Li in the presence of hexane and on hydrolysis it will give acetaldehyde. Fifth, formation of ketones by action with any orthoester other than orthoformic ester or alkyl cyanide. Sixth, formation of nitrile by action with cyanochloride CH3Li plus ClCN. In the presence of hexane, it will give CH3CN plus LiCl. Reaction with alkyl halide. Alkyl lithium react with alkyl halide to form alkanes. For example, ethyl lithium plus CH3 bromine in the presence of hexane, it will give propane. 7. Reaction with aryl halide. Aryl halide undergo nucleophilic substitution reaction by elimination, addition or benzene mechanism. For example, O-fluoroanisole eliminate to give benzene and on addition it will give 3-phenylanisole. 8. Reaction with heterocyclic compound. Heterocyclic compound undergo nucleophilic substitution reaction by bimolecular displacement mechanism. For example, pyridine in the presence of C6H5 lithium at 383 Kelvin, it will give 2-phenylpyridine. Difference from Grignard reagent. Organolithium compound being more reactive than Grignard reagent undergo some additional reactions as discussed below. First, action with carbon dioxide. Grignard reagent yield carboxylic acid with carbon dioxide while organolithium compound yield ketones. The difference is due to the reason that organolithium compounds are more strongly nucleophilic than the Grignard reagent and thus react further with the intermediate resonance stabilized carboxylate anion give ketones. Second, action with carboxylic acid. Alkyl lithium compound react with carboxylic acid, yield ketone as a main product. Grignard reagent on other hand give alkane corresponding to the alkyl group of the Grignard reagent. Third, addition to carbon-carbon double bond. Unlike Grignard reagent, organolithium compound added to simple alkene to give a mixture of compound. The addition occur at a high pressure. Fourth, formation of tertiary alcohol. Organolithium compound being more nucleophilic and smaller in size than the corresponding Grignard reagent add to sterically hindered ketone to form straightly hindered tertiary alcohol. Grignard reagent, on other hand, do not give such addition reaction. For example, isopropyl lithium add to diisopropyl ketone to yield Third, isopropyl carbonol. In contrast, when isopropyl magnesium bromide is added to diisopropyl ketone, the expected tertiary alcohol is not formed. Instead, reduction of the ketone by the Grignard reagent occurred to give diisopropyl carbonyl and propylene. Fifth, reaction with alpha beta unsaturated carbonyl compound. Organolithium compound with more nucleophilic predominantly undergo 1,2 addition to alpha beta unsaturated carbonyl compound, whereas Grignard reagent gives mainly 1,4 addition product. For example, benzyl acetone in the presence of hexane and CH3I, it will give 1,2 addition product, and hydrolysis it will give 2-methyl 4-phenyl butene 3 into all. Thank you.